So this is what? This is JAM 2021. It's question number 15, maths of course. And so it's a function from naturals to naturals, and it's a bijective function. Such that Fn by n square, okay, this thing is finite. Okay? This is all positive, so no problem. The number of such bijections, yeah, how many such F? Yeah, I mean, there are options, but let's try first and see. This question makes sense even without the option, so let's try it. So just to get you into the question, if it's needed, I'll just say, like, if you take F equal to identity, it does not work, right? Because then you get 1 by n, which is not finite. Summation 1 by n is not finite. Harmonic series. So we will take this. Right. So the identity does not work. Is there any function? Is there any bijection that will work? That is the question. Balance with the 1 by n square. So if it is finite, this is a nice question. This doesn't fall into any direct category. Just looking at the options. Right? What do you think? Any ideas? Well, I'm kind of getting the feeling that it should not be possible, right? So why I'm saying is because there is this thing like, formally, I suppose you can call it a rearrangement. rearrangement. But let's just think about this. Think about this lemma type of thing. No, actually, no. If I go into lemmas, it will go all the take a long time. So let me just let's just look at this. So if you take the numbers from 1 up to fix some n, right? Let's fix some k, right? So k square. Okay. And then you have these numbers. Yeah, so what you want to do is you want to right, you have these numbers. From there you look at these numbers. Okay. Correct. Now I'll say more, but let me in the middle say the motivation. What my philosophy here is that, I mean, the n by n square thing is actually minimizing the expression. If you take 2 by 2 square and you take 3 by 3 square, right? Just use like a, I'm using saying common sense, but not in a derogatory way. Okay. Just think logically, right? This is kind of a minimizing thing. Do you feel that? Any permutation in the numerator is sort of will make it bigger. I suppose that you can agree with me, right? Yeah. That's my point. Okay. So to make it more precise, you look at this, and this is a decreasing sequence, right? So I'll just keep it as yeah. Let me write it. So this is a decreasing sequence. And then the other thing you have is 1, 2, 3 till k, right? That is an increasing sequence, correct? Now, if you are asked to take this set and take this set and form that product, paired product, a sum of product of pairs, right? You want to form the sum of product, but product of pairs, right? Or products of matching, right? You need to match. You need to maybe the easiest matching which we talked about, but you can match it in like this crisscross matching, right? And then you can take the product. That will be one product, right? So there are many ways to form the products with all possible matchings, but that's not the point. Point is that which product will give you the minimum answer. The product that will give you the minimum answer, which will be when you take the when you multiply the largest with the smallest, second largest with second smallest. That's the worst way to, increase, right? I think that's, there's a theorem, it's called rearrangement inequality, Abel summation formula. Those are the words, if you Google, you will find everything. Measurization probably also you can chip in, but you can read all that. But if you read it, it's better, and you can tell me, especially the measurization thing, I don't know very well. But common sense, like it's like this should be the smallest should come from there. So if you just focus on the finite part, then all I'm saying is that this okay, it's wrong notation. This thing where j goes from 1 to n, k, is lesser than if you take any permutation, any other, if you do it in any other way. And what will the largest be? The largest also, just analogously, it will be this, when you multiply the smallest with the smallest. Or rather, I should say, when you multiply the largest with the largest, then it sounds like it will be the largest, right? So that way you can think. So this is how it will be, right? This is sort of the smallest, right? Okay, so that's the thing. Now, how do you complete the problem to the infinite case, right? Well, what does this mean? I mean, I need to show. So I show, right? I show that this is infinite, right? And what does that mean? I'll show that this becomes bigger and bigger, correct? So if you fix any k now for the infinite case, think about it. If you fix any k now, you already know that this is true. But the problem is that it can be something like this. Suppose your k is 10, right? But then there could be like here, the numbers don't need to be from 1 to 10. It could come from 1 million. It could be larger, but that would actually make it larger only, na? Right? If you again add till k, and here you put 1 by j square only, right? But here some of the sigma j's you are actually increasing, right? That will actually make it larger than this thing, right? It will make it larger than some permutation, or right? Yeah, it will make it larger than some permutation, right? I'll give you an example, then it should be more clear. And that is enough for it to become larger than some permutation, then it will become larger than this. For example, I'll give you an example. So it's like if it is uh, 5 by 2 square, whatever, 3 by 3 square, 2 by 4 square. Okay, then this is larger than what? I need to first bring it into, bring all these numerators into from 1 to 4. That is not a problem, right? Those which are inside 1 to 4, you keep them. And the rest, ke liye, there are 2 of them, and 2 numbers from 1 to 4 will be remaining. So I can obviously put it. You put it anyhow you want. Doesn't matter. 4 by 3 square. Brought everything inside. Some permutation, so it comes in this category. Now you now you know that this comes into this case, and there this is smaller. So then you can yeah? So it will not be finite for any. Okay. Obviously, it is modulo this thing, and I will frame that as an exercise, and then you can prove it, or you can. Or I'll also give you some reference where you can read and tell me, present me how it is done. Okay. So yeah. But first, you tell me if this is clear. So the answer is no, I think. Yeah, no functions.
Yes.
Okay. Yeah, I mean, look, if you're doing this on your own, it may be that your explanation may not be this clear. Means you may not be able to explain yourself very, very clearly. But right? I mean, you should know that it will work. But yeah, but if you're more clear, then you are more sure. Then it's more and more certain. But then the problem that I want to give you so that you can formalize all this business is something like, it's called the rearrangement inequality. And if I forget, I'll look at the book. I mean, you will find it online, of course, and there. But the book which I like, very fond of when I was studying all this, Secrets in Inequalities. The name is also very nice, but not just that. Something about this book was very special. Means that yeah, I mean, nothing, it was just that, yeah, something about this book is very nice. I mean, that you somehow keeps you going in it. So Rearrangement Inequality, it's by Pham Kim Hong, Vietnamese guy. He has written many books. I mean, it's a bunch of books, but part 1, part 2 is sort of much more involved. But part 1, you can just read it online, but also this book has many interesting matters on this. Rearrangement inequality. Yeah. What is this? It's very simple. You'll find it in any inequality book, any Olympiad book also, but yeah. Yeah, okay.
So the function wala part एक बार और बता दो ना.
Which one? Yeah.
Previous one function.
Which what? Like which part?
The sum of product of नीचे वाला question.
Yes. It will be clear when you do that problem, but yeah, okay. Because that is what will happen then in that problem. So you're asking for the finite case, right? Am I correct? You're asking for the finite case, or
Yes.
this part, right? Then you
okay,
listen.
Totally एक बार.
Okay. So okay, let me let me say the okay, finite case, then you decide. Okay, the finite case you'll better understood if you say in this framework, proper framework. So let a1 a2 till an just be actually the nice thing about it, they don't actually need to be positive. I think it still that works without positive also. This and this be real numbers because you need to compare them. Yeah, these are just in R. Everything is, I mean, there are two sets, but you understand real numbers. Okay. Then and also assume that non-decreasing. So both are non-decreasing. Okay. All right. There are many interesting things in this actually. Yeah, we'll not talk about it now, but now I recall a little bit. Point is that this thing will be the smallest. When you multiply the smallest with the smallest, it will be the smallest. Okay. And that in our setup was, so what was the AIs? You can take any one of those two sets, but you can take like 1 by n square, 1 by n minus 1. Well, it was right. This thing, it's a decreasing sequence. Sorry, increasing sequence. This was our AIs, no? And then your BIs was this, right? And so this I'm saying when you multiply the smallest with the smallest and largest with the largest, this is the largest. And of course, here, when you do the opposite way, when you multiply the smallest with the largest and like that, then again smallest with the largest and the remaining. So it's the same language of smallest with the largest that takes you all the way, AN and BN. That's it. This is the smallest. And in between, you can try out any permutation. It will always be in between, but there is further, you can say, but not now. This. Where sigma is just a permutation. It's not summation over sigma, but sigma is in Sn, right? It's not the identity and it's not the ulta permutation. I mean, you can put identity also, but yeah, because I put greater than equal to, but yeah. I'm saying that you take any other permutation because see, this sum is a sum of product of pairs. This is what it is, right? It is a sum of product of pairs. And pairs here have to be understood matching because you don't want to repeat, you understand, right? You don't want to repeat BIs with two AIs and so on and so on. It's a matching. This. So this is all it is, and that's now that thing is clear, right? Yeah. Infinite case, I can explain, but let me, yeah. But then you should first of all prove this for homework. Try this. Try this on your own, and if you cannot do, then look at these things, and then you can tell me how to do. So this is the thing, and now you see for the infinite case is, I mean, it's the same thing, right? If you have now, if you have infinite case, then I want to, okay. So let me write it more explicitly. So it is like f1 by 1 square, right? f2 by 2 square, fn by n square, let's say. Okay. Then you know that this thing will be bigger than what? This thing will be bigger than g1 by 1 square, g2 by, I'll say what that is, gn by n square. Where what is gi? G is a function which, you know, so g of k, yeah, it is equal to k, yeah. No, it is equal to fk. So I mean, you don't do anything if fk is less than equal to n. Okay, is less than equal to n. So if fk is less than equal to n, then it is same. If fk is less than equal to n, then you don't do anything. You keep the g as it is. Okay, but if fk is greater than n, right? Then gk then gk is equal to you know, like the smallest number which is not, yeah, so it's just some s, right? It is some s such that s is less than n, s is less than equal to n, and this condition, right? And s is not equal to g of I for I less than k. right? So if from 1 up to k minus 1, whatever things were used, you don't use them, and you use the next thing. Okay, but actually this is wrong. Now I can write, but I'll not write. I'll just say it and say it. What I'm just saying, okay, let's forget the G. Okay, yeah, what I'm just saying is that if you see some f2, right? If it is less than n, you keep f2 here only, and if f2 is bigger than n, then just replace it with something which is less than n. Okay, and with the condition that it is not equal to any of the other things, any of the other FIs, and that will always, you can manage, right? You'll always have, because there are n numbers and n options, something, so you will always be able to do that, right? So you will come down to this, and that's the thing. And this, then what you will get here will be a permutation, and certainly this will decrease, because that's clear, you're just decreasing some term, or you're keeping it fixed. But this, you know, by this rearrangement inequality is of course bigger than this summation n by k square, which is summation 1 by k, right? So this is bigger than summation 1 by k, but summation 1 by k can be made bigger than any m you want, provided you take n large enough. So this is bigger than any m you want, and so it is infinite. If you increase the n, you can make it bigger than anything you want. That's what infinity means in this case, right? That's what limit being infinite means. That's it. So it's a finite argument. It's an infinite sum, but the argument is finite, right? Like f of 1, like 1. So in f, the output of 1 may come at 10 million, but it will come, right? But that is not sort of important for us. That actually is the other way maybe, but anyways, yeah. I mean, every number comes in this bijection, and main thing is actually not that. Main thing is that it doesn't repeat any numbers. Yeah, doesn't repeat any numbers. So actually, this question is sort of this thing. You can replace it by injection, but actually that's a foolish thing to do, in the sense that it doesn't make a problem harder. But even if you have some injection, it will still be, answer will be same. I mean, that's what the proof tells us, right? You never use the fact that it's surjective. You just use the fact that it's injective. Where did I use the fact that it's injective? When I said that if this f2 is n plus 1, I said you replace it by something less, right? I said you replace it by something less. That's where you're using injection, right? Because you want to replace it by something less. Um, no, wait. Yeah, you're actually, wait a minute. Okay,
तुमने
so
permutation कहाँ से आ रहे हो समझ नहीं आ रहा।
you're making the numbers distinct, right? That's how you get the permutation. It was a bijection, right? No,
Yes.
so that's how you get the permutations. So it's like, I mean, so it's like if you have 1, 5, 2, 9, 7, 1 square, 2 square, 3 square, 4 square, 5 square. Then I will change this to, I said this thing, right? So this is 2 square, right? So I don't want, okay, there are 5 things, so I have 5 square is fine. Okay. 2 is also less than 5, so it is fine, right? I'm just putting a plus. Now when you put 4 square, I don't want 9. I want something less than 5. Is there space for that? Is there something less than 5 present? Which is left? Yeah, 3. Put 3.
See,
Just that, right? I'm just doing that. Nothing. 4. You get a permutation. If I have a permutation, then I can reason, then I can use a rearrangement reasoning, so that this numerator will be from 1 to n. You see my point? If I don't bring the numerator from 1 to n and the denominator from 1 to n, then how can I apply that rearrangement thing? Is that correct?
yeah, got it.
Right. But actually, I mean, maybe that's why a little confusing, because actually you don't maybe, yeah, you don't need that. You don't means I've reasoned it like this, but actually it's slightly unnecessary, right? Yeah. And it's unnecessary because what you can just say is that these are the numbers, right? And then what you do is you just change this in a non, you just permute them in a non, I mean, just rearrange them in an increasing order. Okay, don't make it a permutation, just rearrange them in an increasing order. 1 2 9 1 2 5 7 9. Okay, you can say like this also, right? Then the number will decrease. That is by the rearrangement inequality. Because again, these are, if you, these are in increasing order and these are in decreasing order, so the product will be minimized. So this, so if you replace this thing with this thing, where by 1 square, by 2 square, by 3 square, by 4 square, by 5 square, the summation will decrease, correct? And now this thing will be bigger than, obviously, right? This will be bigger than 1 by 1 square, 2 by 2 square, 3 by 3 square, and so on, right? Because the third term will be at least 3, right? Because it's a bijection. Fn was a bijection. But it's enough that Fn is an injection also for this to happen. Agree? Even if it's an injection, you know that this will be distinct and they'll be increasing order. So the kth thing will be bigger than k. So it will be bigger than this. That's why I said the problem may injection is enough. Surjection is surjection is not enough. Yeah. Yeah. Okay. I will take it back.
But I guess surjection is they're using just because they don't want any repetition of numbers, right?
No, but that is coming from injection, right? That's coming from, so, see, injection is enough. That I'm 100% sure that if the question is replaced by injection, the thing is true. But if the question is replaced by surjection, then it will not be true. I'll give you some examples next time. Okay, it's a funny word. Yeah, it will not be true. I can say, but I'll not say now. Okay. Yeah. If you replace it by surjection, it's not true. And that is some sort of a very slowly decreasing, slowly increasing. You can make this thing very slowly increasing. You see my point, right? If your Fn is 1 1 1 1 1, sort of, long 2 to the power n times, and then it is 2 2 2 2 2 to the power n square times, right? You see my point, right? This will be a surjection, but the summation will not become infinite, right? You can think why. That is related to, so you must have seen Cauchy condensation test and so on, right? How you prove that this thing is finite and that thing is, how you prove 1 by n square is infinite? You do something like this, right? You pair them and powers of 2s and group, and this kind of trick you can say to it. Surjection will not be enough, injection will be enough, but you should take that as homework and try to prove that if it's surjection, then there is a surjection for which it is finite. And yeah, anyways, you do all that, lots of work to do, and then we'll see. We'll meet next time and see. Okay. All right. We'll stop. Okay. I'm leaving it like this, and there's a way of doing on, but I think Arnav will not be joining, so we'll do on Thursday. Okay. Bye.